Okay, welcome back. Okay, we start with the potential energy. Okay, just to recap of what we have covered last time. Okay, work of the force exerted by the spring, you can see it, depends only on the initial and final deflection of the spring. Okay, so so we have here work done from 1 to 2 is equal to half kx1 minus half kx2 square. Okay, all right, and then another statement over here, we have the potential energy of the body with respect to the elastic force. Okay, so we have here VE, okay, which is E stands for elastic. So we have potential energy of the body, okay, with respect to elastic force equal to half kx square. So when we want to relate with work done, okay, from 1 to 2, we're going to have potential energy of the body 1, okay, minus potential energy of body 2. Okay, so we have done this one in our last class. Okay. And just to recap of what we did last time, also I have discussed with you the concept of conservative forces. Okay, so a force is conservative if its work, okay, 1 to 2, okay, u1 to 2 is independent of the path, okay, followed by the particle as it moves, okay, from A1 to A2. You can see this figure here, A, okay, it can go this way, okay, this independent of the path, it can go this way, can go this way, right, but they reach the same destination, okay. Gravity force and elastic spring forces, they are conservative, okay, and friction forces, they are non-conservative. Okay, this is what we did last time. So I okay, we continue. Sorry for the interruption. And then we look at another concept, which is conservation of energy. Okay, so what we have here, the concept of conservation of energy, I've given to you the work, okay, for a conservative force. Okay, so what we have here is work done from 1 to 2, okay, equal to V1 minus V2. Okay, so we are having this example just to show you how we can apply this concept. Okay, the energy conserved. Okay, we have principle of work and energy here. Okay, work done, T2 minus T1, and also it will follow when we say it is conserved. This is not new to you, the concept. We have T1 plus V1 equal to T2 plus V2. So we denote this as E equal to T1 plus T plus V, which is equal to constant. Okay. these are the detail of how we can relate or get the value of this problem. Okay, so we have T2, which is half mv square. Okay, and then we got in the value here. Okay, over here B2 is 0, and then T2 plus B2 equal to WL. Okay, this is an example of conservation of energy. Okay, we have the block here is going down. Okay, going down and then going up the hill. Okay, so this package or this block, it has the velocity v. Okay, velocity v at one location, and then this is a prime. Okay, and then here is a double prime. So this particle is moving along the path. Okay, we have stated here that we have no friction, okay, applied for the package. Therefore, the total mechanical energy is constant. Okay, so the only thing here we have is the potential energy. Okay, potential energy is depend on the elevation. So we have the dotted line here. Okay, is the say this is the datum. So it depend on the elevation. Okay, from here and then here. Okay, depend on the elevation, and also the particle speed, if you can see here, is the same at any elevation. At this elevation A prime and A double prime. Okay. Okay, for our next slide. Okay, for our next slide, we're going to go through this example. Okay, I want you to read this example. Okay, for 1 minute. We try to understand how the nature of this problem. Okay, because what you can see here is the problem we have here is related to what? What kind of problem that we have? Yeah. It's related to the spring, right? Spring. Okay. 20 pound collar slide without friction. Okay, along a vertical rod. You can see the figure on the right here. We have the spring. This is the original location of it, right? So the spring. Okay, before stretch. Okay, before stretch is given here. The length of it before deflect, the length is 4. After you stretch it, the length of it is 8 inches. Okay, 8 inches. Okay, so you have here, if here is 8, this is 6. So what is the length of this one? What's the length of this one? Can use the Pythagoras theorem, right? 3, 4, 5, right? 6, 8, 6, 8, and then 6, 8, and 10. Right? So this is the length. Okay, 6, 8, and 10. This length is 10. Okay, so you are required to find the velocity after it have moved 6 inch in the position of 2. Okay, so we have position 1 here, and then we have here the position of 2. All right. Okay. All right, I want want to see your comment here. Yes, yes, 10, 10. Oh, good, good. So if okay, okay, 3, 4, 5, 6, 8, 10. Good. So we proceed to how to solve the problem, right? Okay. Can you see the slide? What do you see? Just want to double check.
Position 1, position 2,
Okay,
conservation of
okay.
energy.
All right, thank you. Okay, okay. Because right now I'm reading your comment. How come you get 12? If 8, 8, 6, 8, 10, right? 6, 8, 10. 6, 8, 10. 3, 4, 5. Okay. If 12, 13, 12, 13. Okay, not 18. 12, 13. Okay. Okay, now we're going to do this to find the solution of it, okay, step by step. Okay, let me see my pen. Okay, this is my pen. Okay, going to start. Okay, so what you need to do here, okay, we have to apply the principle of conservation of energy between position 1 and 2. Okay. Okay. Something. Sorry. Okay. Okay. So what we have here, this is we have a datum here. Okay, this is a datum 1, and here is datum 2. Okay, so as I mentioned just now, the caller, okay, has an undeflected length, so we have to start with that. Okay, position 1, so x1, okay, x1, so we have 8 inches. Okay, so we write 8 inches like that. 8 inches minus 4 inches. Okay, so what do you get? 8 minus 4 inches, so you get 4 inches. Okay, this is x1, and then after you obtain that one, okay, we want to find the value of VE. Okay, so VE at position 1, so we have VE. Okay, what is VE? Formula of VE, this is elastic, right? It is kinetic energy. So Kx 1, 5. Okay, so you substitute this x1 here. Okay, so you get half. Okay, what is the value of k is given in the problem. Okay, it's given in the problem, which is 3 pound. Okay, the unit is in inch, right? 3 pound, and then multiply by 8 inch minus 4 inch. Okay, sorry, this is 4 inch. Okay, square, right? Half kx square. So what do you get? The answer, half times 3 times 8 minus 4 square. So 4 square. 4 square times 3 divided by 2.
6.
16 times 3, 48. 48 divided by 2. Okay. Where 8 minus 4, as I mentioned just now, we stretch, right? We have stretch. The original length of the spring before we stretch is 4. So when you stretch, okay, so 8 minus 4, the deflection, okay, how it deflects, how we stretch. So it's 4 inch. So you get 24 inch, okay. So you have here, I use different color. Okay. So we have here 24, okay, inch span. Sometimes for inch, as I mentioned just now, 1 inch, we use this. For pound, we use hashtag. Okay, one foot equal to 12 inch. Okay, satu kaki 1 foot equal to 12 inches. Okay, okay, and then you can apply the formula here. Okay, V1 equal to VE plus VG. Okay, so VE plus VG. So we have here 24 inch. Okay, this one is 0, so you have 24 inch pound. Okay, plus 0. So you can convert this one to be in foot pound. Okay, foot pound. So it's going to be 12. This one divided by 2. Okay, 24 divided by 12. So you get 2. Okay, 2 foot pound. Okay, this is V1. All right. How about T1? What is the value of T1? Okay, if you look at here, at this location, we have here V1, right? Okay, this is V1. If V1 equal to 0, what will be T1? Oh, Hani say 0. Okay, 0. Shazwan say 0. What else? What else? Any other answer?
Because there is no kinetic energy.
No kinetic energy. Yes. So we have the value there. T1. T1 equals to 0. Okay. T1 is 0. Right. We have completed the first part, which is position 1. Okay. Now we proceed to position 2. Okay. Look at position 2 here. Okay. This is position 2. From position 1 to position 2. Okay. So it's going down like that. And the spring has been stretched in this manner. Okay. Right. Okay, so we have here position 2. For position 2, same thing. We have to look at the elongation. Okay, the elongation of the spring. Okay, okay, we have the elongation of the spring. Position 2. So we have x2. Okay, at this elongation, the length of the spring is 10. Okay, 10 inch minus what? 8 minus what?
10 minus 8.
Minus 8, no.
4.
Minus what?
10.
Minus 8, minus 6, minus 4. Which one?
Oh. 4.
4. Any other answer? You must deduct with the original length of the spring. Okay? The spring, maknanya without any stretch, without any displacement, right? The original length. Kan? 8, 6, 10 tu after the stretch. Right? So at datum 1 tadi, for x1, we deduct by 4. Right? So for this time also, we have to deduct by 4. Right? The original length of it. Okay? Make sure. This is 8 minus 4 inch. So you get 6. Okay? 6 inches. Right. So we proceed to find VE. Okay. So in this case, VE. Okay, VE equal to half kx2 square. So you get half multiplied by 3. So the unit is, remember, unit is pound per inch. Okay, still pound per inch. All right, and then multiply by 10 minus 4 inches square. Okay, so what do you get? 6 square, 36. 36 times 3, and then divide by 2.
54.
54. What's the unit? 54
pound per
Pound.
inch.
Pound inch.
inch.
Pound
Pound,
inch.
pound.
Okay,
In
pound inch.
pound.
Okay, so you have 54 pounds inch. Okay, don't convert it yet. Okay, we proceed to the next one. Okay, just now. This time we have VG. Before this, no VG because we set the datum, right? Set the datum over here, the datum, so meaning no elevation. Okay, we set the datum here 0 here. So the datum here is 0. Okay, no elevation here. That's why datum means 0, 0, right? And then VG. Okay, this time we find VG. Okay, how to get VG? All right, we find VG. Okay, so VG. What is the formula of VG? VG is W times Y. Okay, so what is W?
Mass time gravity.
What is W?
Mg.
What is the value of W?
20 pound.
Given, right? The red in
Yes.
color here.
Yeah.
You're given there 20 pound. Okay, 20 pound. 20 pound times Y.
6. 6.
-6.
6.
Nah, negative 6. Negative 6.
6 ke minus 6?
Minus 6. Minus 6.
Minus.
That's why datum very important, right? So
Sorry, sir.
the datum is very important. So make sure you choose the right direction. The datum, right? Bukan rectum, datum. So going down is negative, right? So we have here minus 6 inch. Okay, minus 6 inch. So you get minus 120 inch pound, right? Okay, we finish there, and then what we need to do then? We write down VU equal to VE plus VG. Okay, so what do you get? 54. You get 54 minus 120, which is
Minus 66.
minus 66 inch pound. Okay, we want to convert to foot pound, you divide by 12, right? 66 divided by 12. What do you get?
5.5, sir.
A minus 5.5.
Minus 5.5.
5.5. Foot pound. Okay. Foot pound. Okay, we have done the second part of it, which is the position 2. Okay. So we haven't finished yet for that one. We need to find T2 now. What is T2? You know that T2 is half mv half mv2 square. Okay, so you have half time, we have 20 pound, right? M to convert 20 pound, you must divide by 32.2. Okay, this is an SI, and then times V2 square. Okay, so use your calculator. What do you get? You're going to get in terms of V2 square. Okay. Any answer? Nobody try?
0.311 B square.
20 divided by 2 divided by 32.2. 0.3, okay. 0.31. Okay, 0.31. But the value of V still unknown, right? With 0. Okay, V2 square. Okay. Okay. This is for position 2. The following step is we have to find the conservation of energy. Use the conservation of energy. Okay, so we are applying here conservation of energy. Okay, I'm using another color. Which color that you want? Okay, we try to have a
Pink, sir. Pink.
pink. Pink.
Ah,
Oh, pink. No pink. No pink color here.
magenta.
Alright. We use a universal color. Okay. Okay. Conservation energy. Please tell me what is the formula of conservation of energy? T1 plus V1 equal to T2 plus V2, right? So you just plot in what you have obtained earlier. So what is T1? What is T1? T1?
0.
0. This is 0 plus V1. We put in foot pound, huh?
2 foot pound.
2. Okay, 2. Okay, and then
0.
T2. T2 is the one that we obtained just now, which is
0.31
0.311 V2 square. And then what is V2?
negative 5.
Negative 5.5, right? Negative 5.5 foot pound. Okay. Okay, now you solve for V. Solve for V2. Okay. So what do you get for V2? You get plus minus, right? You get 4.91. Okay. Foot per second. So which direction? Going up or going down? The velocity of 2. This velocity, of course, is going down, right?
Yes.
Yeah, going down. So the direction going down. All right. So we have done this one. Okay. Our next thing that I'm going to highlight here. Okay. For this example, do you have any question before we move to other agenda? Any question?
Sir, in conservation energy, program tak ada ke?
Conservation of energy.
U122.
So what the question asks you to do? That's why I need to look at the problem, because we are doing the topic of conservation energy. Okay. So we need to find the velocity, right? Velocity after by applying the concept of conservation of energy. Potential energy. We are using potential energy, and the concept of conservation of energy. So we have to relate between kinetic energy and potential energy. Okay.